So good morning, everybody. I'm Mark Moll, Director of Research at PickNik Robotics, and also a... Sorry? Can everybody hear me okay? Yep. And I'm also the research scientist at Rice University, and I'm interested in theoretically sound but practically useful algorithms for robot motion planning. So I'll tell you a little bit about the Open Motion Planning Library, which is the default planning library in MoveIt. So I'll give a very brief overview of what OMPL is, and then give describe some latest developments that we are in the process of bringing to MoveIt. So this is sort of a sneak preview of good things that are sort of being tech transferred from academically sound ideas to being fully integrated and usable on real robots. All right, so a little bit of a very brief overview of OMPL. OMPL was written as a generic robot motion planning library. It's focused on sampling-based algorithms, but we always had this idea like, well, eventually we want to be able to add other kinds of planning algorithms to it. That hasn't really happened yet. Everybody wants to sort of have their own brand of library, which is fine, but API supports other kinds of planning approaches. So one of the surprising things for many people who first look at OMPL is like, there's no description of a robot, there's no description of an environment. That's like by design that we've abstracted that away because there's many ways that people would like to model different things, many different ways that people like to do IK. So we've left that out, and basically that means that OMPL by itself is not very useful if you want to do this or do motion planning on a real robot. You really need a larger robotics framework around it to handle kinematics and integration with perception and control. So obviously MoveIt is the most well-known version of this, but there are other planning frameworks out there, or robotics software frameworks that have integrated OMPL. And the fact that we are able to sort of integrate with very different kinds of approaches for robotics, robot motion planning indicates that maybe we've hit an appropriate level of abstraction. Like many open source projects, it's very hard to gauge what the impact is and how many people are actually using it. These are sort of rough, just like Dave showed some statistics on how many people are using MoveIt. This is sort of a similar slide. They probably have an optional registration process if people build from source. So we have a few thousand people who choose to register, which is a very small fraction. Most people don't want to fill out web forms, or they just apt-get install a package and they'd rather be done with that. But besides, so that's how most people get their version of OMPL, just through MoveIt by just their package manager. But additionally, we also have 70,000 downloads. We have 800 citations, even more than MoveIt. Since we started counting web analytics, millions of page views. So one thing that I feel very strongly about is benchmarking. So that's you don't necessarily have to believe me that planner X is the best one for problem Y. We really want you to run your own experiments and validate this for yourself, because the right planner is really very problem dependent. So we've built a lot of infrastructure to analyze performance, collect lots of performance characteristics, not just like how long does it take, and build ways that you can get a sort of statistical description that you can interactively explore. A lot of this stuff, other people thought it was a good idea too, so it has been migrated to MoveIt. So the same kind of web-based analysis that you can do on your performance is now also possible with MoveIt data. So you can essentially run MoveIt, collect a whole bunch of statistics on representative problems for a particular domain with robots of interest, and then afterwards look at like, in general, which robot can give me solve time in less than this many seconds 90% of the time, or what is the average path length or median path length that might be relevant for your application. Or for optimizing planners, it's very interesting to look at convergence rates. Like, what is the guarantee that you can give on? That's these kinds of plots. So different planners showing how they converge to some optimal path, and be able to sort of say, well, with confidence, like, oh, what is the kind of performance I can guarantee after this many seconds of running my planner? So that actually brings me to the first part, planning with costs. So there's a lot of interest in trying to create optimal motions. And that's kind of the first, that's kind of a whole can of worms in itself, because really what we mean by optimal motion means very different things to many different people. Many people think of this as, oh, it's easy. It's just, whatever is the shortest way to get from A to B. But the shortest really depends on what is your distance metric. And usually when people are doing motion planning, they're planning in configuration space. So this can be a very short motion, because I'm just moving one joint. But really what people mean when they say short, like, well, maybe it's displaced volume, something that's more like I'm moving all the joints, but the volume of my arm swept through space is minimized. But that's expensive to compute. So if you want to minimize that, then you pay the price in longer solve time. Or people say, well, actually, I guess I want a short path, but I also want it to be smooth. And I also want to be a little bit away from obstacles. I don't want to graze obstacles. So before you know it, you said, okay, actually, it becomes a much more complicated problem. So we needed to add the infrastructure to express all these different things that you might want. So here's a very simple example where you just have one obstacle and a point robot moving in 2D, and the boundaries don't count as obstacle. You want the shortest path, you get something that gets closer and closer to this circular obstacle. You say, oh, I want clearance, and you want to be as far away as possible but get to the goal. Then you get a path that sort of converges like this. And here's a way that you can sort of express some combination of that. Some heuristically defined combination of clearance and path length. So we build up this infrastructure in expressing costs, like what does it mean for a path to be low cost, that it can be optimized. So that means that we can say, well, we have a way to define cost per state. So you can imagine that we're basically traveling through a cost landscape, and we try to sort of go over hills and try to find a minimum path that mostly goes through valleys in this cost landscape. Additionally, you can define cost so basically to get between states, so a motion cost, it can be path length, and then there's different ways that you can aggregate costs. Again, this sort of may seem a little abstract. It's like, well, why do we need that? Maybe I always want to minimize path length, which is usually just the sum of these path lengths between segments. But in cases you want to minimize or maximize the minimum clearance, then you have something that's a different way of aggregating costs, and a larger clearance is better. Right? So we need to sort of express sort of an algebra over costs. So that's what we've added to OMPL. And then additionally, maybe we want to have terminal costs that basically what if I define different graphs, certain graphs are better than others, so you can define these graphs with goal states, and we may associate a terminal cost with that. All these things can be expressed. We have admissible heuristics that you can use inside your planning algorithm, but this is completely agnostic of a particular planning approach. This just allows you to express what is the cost of a path or a motion. But many planning algorithms have been extended to exploit this, and many others can be added to that. And most of the post-processing tools that we have in OMPL to sort of clean up your path are sort of cost-aware. Typically, whenever you get a path from a randomized algorithm, there will be little random motions in there, and we try to sort of smooth it out afterwards. But in the process of smoothing it out, we try to do this in a way that basically always lowers the cost. Right? So you don't want your path necessarily to become simpler, but actually worse in cost. So there are many ways to do this. One counterintuitive way that we came across is it's sort of like it's better to just keep banging your head against the wall and try to repeatedly run a planner and find a feasible path each time. Feasible, not necessarily optimal. So don't even try to find an optimal path. Just repeatedly try to find a feasible path. Now you have a bag of plans that all are feasible, but none of them are optimal. But if you somehow sort of stitch different parts together of these paths, like the chances that all of them are unlucky all of the time is pretty slim. All of them are sometimes make a reasonably optimal motion. So by just sort of stitching together a collection of paths, we can extract from that one path that is a lot more optimal. So we have a very simple approach to just repeatedly run this, and sort of it acts as sort of a meta planner that very effectively creates high quality paths that converge to optimal much faster than algorithms that have been specifically designed for that. So this, basically, this is sort of crossing over into other approaches that Dave already briefly mentioned. So sampling-based planning is very quick and fast at finding feasible plans, but converging to optimal with sampling-based planning tends to be kind of slow. So in response to that, alternative approaches have been proposed that do trajectory optimization that are more local but are very fast. And essentially, you compute a gradient over a whole trajectory that often is initially a straight line path, and then you converge to something that is almost collision-free. The problem is that these trajectory optimization methods treat hard constraints like collisions as soft constraints. It's just, rather than it's forbidden to go through obstacles, it's, well, you just pay a little bit more cost. So sometimes the short path through a thin obstacle is preferable over a long path that goes around it. So that's not ideal. So we found that a really good way to get the best of both worlds is first find a feasible plan with OMPL, and then run it through a trajectory optimization method like CHOM, TrajOpt, or many others, and that will give you a path that is guaranteed to be feasible and almost locally optimal. So that's now possible to do in MoveIt. Basically, you run the OMPL pipeline, and you have this planning request adapter that basically now you pass in that you want to post-process this path with trajectory optimization. And these trajectory optimizers are really, really fast, so it's basically an epsilon extra cost to just apply that. All right, so now this is actually a really exciting topic, at least for me. This is something we've been working on for quite some time. So you can think of this as a Cartesian planning. Like everybody wants Cartesian planning. I want my robot to weld. I want my robot to do sanding, or very, constrained motions. Maybe open a door in some way, respecting the kinematics of the door. All of that is a version of constrained planning. So here I'm showing a simple 3-DOF planar arm, and it's constrained to move with the end effector along a circle. What that means in configuration space is that we have this 3 degrees of freedom, and the constraint induces this implicit manifold. Well, in this case, we may be able to solve it analytically, but in general, we have a low-dimensional manifold of configurations where the constraint is satisfied. And we want to plan on that manifold. So a common approach is to say, well, I'll just use my IK solver. That's, well, it's a way to find individual states, but it's not a way to really map out whatever is reachable. So we've been working on solving this problem with different constraint satisfaction technologies, approaches, and abstracted that from the planning. So you can use different ways of solving constraints and finding sort of tangent spaces along this manifold and walk along this manifold, and the planning algorithms don't even know that you are planning with constraint. They just treat it as this is some implicitly defined space, and we're just walking around in that space. All right, so now we have this, this crazy robot that is just defined as a collection of points as the joints, and we just say, oh, there's distance constraints to sort of keep them from the same distance apart from each other, as a really ridiculous way of defining kinematics, just to create an artificially hard planning problem. And all of these arms are connected to this disk at the end, and it has to move from all the way down to all the way up. So it's a, sort of a torture test to show, like, hey, this approach is scalable. You have over 160 degrees of freedom. You have lots of constraints. It's not possible to visualize what the space might look like. It's not possible to analytically solve this, but we can still effectively move around in this space. Of course, this may not matter to you very much, but hopefully you can see that this is still practically useful with, for applications like Robonaut 2. We've been working with NASA JC on getting algorithms running on their Robonaut. This is operating in 0G. It's climbing around on handrails in the International Space Station, and has to perform routine tasks that are currently done by astronauts. Oftentimes, you're also dealing with closed-loop constraints. So we have a kinematic tree with 4 limbs. Many limbs are often constrained at the same time, and we want to move around in that. So this is a short video showing what that might look like. So this is a one-to-one mock-up of part of this International Space Station. It has to turn a valve, slide the door open, take a few more steps, and then reach for this bag that's shown over there. Press on a buckle, get the bag out, and then walk back. So each time one of the limbs touches, we have another constraint, and it's sort of hard to see, but there's this gravity offload mechanism which introduces another constraint. So you have to keep the torso upright, one constraint, and keep end effectors in different places. Each time we end effector touches, it's a constraint. So now it's sort of turning this valve, And the coolest motion comes after that, where it's sort of sliding the door and moving its whole body along with it. So that's a very complex problem that is, and that's we're working on. So this is running MoveIt, but now we basically created sort of a custom way to sort of embed this functionality in OMPL within MoveIt, but we're working on generalizing this and making it work for arbitrary robots. So that's coming. Buzzing here. That's okay. But yeah, this is to me is very exciting. It's a lot of work, but it provides a nice abstraction. And so if you provide the right hooks for specifying constraints, then actually the planners don't need to know about it because we just create this new space that supports all the different the usual properties that are associated with planning in some search space. You can measure distance, you can interpolate, and all the sort of technical details of satisfying the constraints are sort of handled under the hood. So last topic that I wanted to talk about that's also relatively new, presented at ICRA earlier this year, is on planning with multiple constraints, multiple goals. So this is something that often comes up when you're giving high-level specifications to a robot, where basically we're saying, oh, we want to pick up any of these white cubes, and we don't care which one. Of course, you can treat this as, oh, now we have n problems for n different cubes that we've been detected. We can run our planner n different times. But it seems much more preferable to just say, let the planner figure out which one is easiest to reach, and basically grab that one. But for me, as a human, to guess which one is most accessible to a robot is very hard to determine, because I don't really know what the kinematics of this robot is. I mean, it has a 7-degree of freedom arm and then a joint in the torso. So it's very difficult for me to reason about which one is most easily accessible. So we've worked on some algorithms to make this possible. Actually, so this is kind of an important note that sometimes just the fact that you have an IK solution, like here are some regions that are, IK solution exists, but it's not reachable. So just being able to generate IK solutions is not sufficient. Right? So we actually have an intelligent way of biasing a planner towards things where IK solutions exist, they appear to be close by, and they are reachable from wherever we are. This is useful, obviously for sort of pick and place type tasks when there are multiple objects that you could be picking, just to show that it's not just for that. We also did some tests with sort of car-like systems for automated valet parking, where you have a number of free parking spots, and we just say, okay, park in any free spot, I don't care. And it figures out on its own which one is easiest to park in. Okay, so planning with cost is done. It's available now, it works. Maybe not terribly well documented, but that's it's functional in MoveIt right now. Planning with constraints can be done with MoveIt, but it still requires further work before it's generally useful for multiple goals. We don't have a timeline just yet, but that's not as much work, I think, as planning with constraints. Just to wrap things up, this is done in collaboration with many people. I want to thank Johan, Lydia, and Julia at Waymo, Rice, and NASA, my longtime collaborators and friends. Most of the work was done by students and postdocs, namely Zach, Luis, Bryce, Ryan, and Juan David. And funding is from NSF and NASA. So I'll stop here. Yes. It's funny that you mentioned it. It was actually for some of our client work, we were doing exactly that. And the initial intent was like, oh yeah, we just want to benchmark different motion planning algorithms. But now we're starting to look much bigger and, well, actually we want to benchmark many other things. So for now, that's sort of, well, maybe this could be generalized, but we set it up in a way that it's already pretty extensible, this benchmarking infrastructure. You can basically have documented the log format and document database schema that basically you pipe the logs into that schema, and you can just easily add new columns to a table, and automatically the Plan Arena website, planarena.org, you can upload these new databases and will automatically discover, oh, there's new properties available, and we can just visualize that as well. So there's definitely more work to be done. It's right now sort of not the perfect fit for plotting everything, but that's definitely something that's of interest. Yeah. We welcome PRs on that.
Do you have any more questions? Great.
Oh, one more.
What is most interesting to get the constraint stuff? I mean, is it really meaningful or a minor piece of information?
I think it's trying to identify the right entry points that cover most use cases. Trying to find, because it's nice to say, oh, we can handle arbitrary constraints, but that's for most end users not very helpful. But how do I express these constraints in YAML files and like that? Something that doesn't require me to define custom classes and all kinds of solvers. If you can say, well, it's easy to express maybe end effect constraints are the most obvious ones. Pipeline custom common end effect constraints. Exploit that there already is an IK solver there that basically can be used as part of the approach to navigate along some constraints. That's sort of like, you want to use as much as possible the existing classes that are already there and allow that, combine that in a way that we can express common use cases, but still have maybe a code level entry point too. People want to just define more complex constraints that are not usually covered by some generic things.
It's actually one of the things I'm most excited about, like MoveIt and OMPL. To me, the master branch of MoveIt has really enabled us to change message types, change a lot of these interfaces, break the guy and start to expose these incredible things that OMPL can do.
Yeah. I think there's. I think you did this recently, right? Where you added the sort of reference trajectories to. Yeah.
Yeah, that was a community effort.
Yeah.
Led by Wednesday.
Okay.
Yeah.
So that's you can think of that as a one type of constraint that you may want to consider.
Absolutely.
Yeah.
Oh, yeah. Okay.
So in the constraint, did you update OMPL, both OMPL and MoveIt for class or interface, or you just include add the new features to the MoveIt?
Right now, it exists as a released feature in OMPL, and the demos that I showed, not the NASA robot, but the other sort of more toy examples, you can run for yourself. You can regenerate those movies if you like. That's completely done. But the integration with MoveIt, it requires more work. So right now, it's done for like one specific robot and specific constraints for that robot, and we want to generalize that and make it more generally useful so that somebody doesn't have to write code for every different constraint type.